Hello and welcome to our webinar, Enhance Brake Disc Quality While Coordinating Laser Cladding and Grinding Matters. My name is Dominik Grimminger. I'm the product manager for the coated brake disc at the EMAG Group.
And also from my side, warm welcome. My name is Marina Manger. I work in the technology sales department and take care for the grinding machine. If you have any questions, please feel free to put them in the chat or in the question board. We try to answer them.
Okay, we have 5 categories today. We start with an overview about the regulation and background of the coated brake disc. I will continue with laser coating. Marina will go deeper into the grinding process and the quality requirement of the process chain and data management. And I will complete the webinar with results of the process optimization by EMAG. So I have a small overview about the process steps of the brake disc. We start on the top side with the turning process. I would say every brake disc are pre-turned, and on a conventional brake disc we have 2 options. In Europe, mainly we have the finished turning operation, where we have in the Asian region often a grinding process. When we have a look on the coating side, there are some other alternative process to coat the brake disc, but we focus on laser coating. We have single-layer and multi-layer systems, and both requires a grinding process. Why are we talk about coated brake disc? Everything starts with the GTR 24. This is an international regulation or norm where it's regulate the emissions of brake disc and the wheels. We have here 2 first movers, like the European Union starts with the Euro 7 regulation. The Euro 7 regulation regulates the PM10 emission for passenger cars with, up to 7 milligram per kilometer, and for electric vehicles up to 3 milligram per kilometers. The Euro 7 regulation starts in November 2027 for all types of passenger cars. The same we have on the truck side, but on the truck side it's not fixed yet which emissions are allowed. In China also we see a lot of movement, and in China we have the National 7 standard, where is under the draft, and it should be published within this year and will come into force between 2028 and 2030. So back to our process steps. What can we do with our EMAG machine to fulfill the regulation? As an EMAG, we have all 3 main process steps like turning, laser coating, and grinding in-house. Have a closer look on the laser coating process and the machine. Here you see our process module. The EMAG solution, or we have the EMAG solution as single cells or modules. Each module can be modified or configured by your needs. This means we can add different kind of layers, different kind of lasers. We can add quality measuring sensors and so on. On the front side, we have the control panel where the worker have an overview about the machine and the process. And on the back side, we have the loading and unloading situation. This concept helps to minimize the non-productive times. This means we have really fast change over times between the process steps. And with this concept, for loading and unloading on the backside, we have several options like a manual loading, like a robot loading, or a gantry loading. Now we go a little bit deeper into the process module. In addition to the mechanical engineering, we have also a monitoring inside. This means our quality software collects all data from the machine and from our sensors and collect them and gives an overview about all numbers. The powder gas stream analyze monitors the condition of the nozzle and helps to align the powder cone to the process. We also have the weld pool monitoring. It's a camera who looks directly through the optic into the process. The melt pool monitoring checks the intensity of the melt pool and also the size of the melt pool. Both features together helps us to align laser spot and powder spot to increase the powder efficiency. On the right side, we have the layer thickness sensor, where we can measure directly in the process the layer thickness and also detect the deformation of the part. We have the options with our process modules to put them together, like a single, dual, or three station machine, and we can link them with different kind of automation systems. Here we see now the process or the finished layer. Here we have a crosscut through the complete brake disc with the layers. We start from the bottom. Here we have the gray cast iron. Then we have our bonding layer with a stainless steel matrix. Normally the customer choose layer thickness between 100 microns and 150 microns. The last layer are the friction layer with a mix of titanium carbides and stainless steel. Approximate layer thickness is around 250 microns. We have options of several or different kind of titanium carbides, but we see in the market a lot of movement into variations of titanium carbides, or not only the standard titanium carbides. Not allowed in our layer systems are pores or cracks or delamination. And this is, from our point of view, a good example how a good layer quality should look like. Even we have here a really good surface roughness. It's not fits directly into the car, because of this layer thickness variation, we need an additional process step. And in the EMAG group, we choose the grinding process in this case. Now we have a short movie, how the machine and the different process steps looks like. This is our plant in Heubach, where the laser coating machines are mounted. You see here the backside of the machine, here in this case manual loading, but it's also an option to have robotic gantry loading. In this case, we have two process modules. We are linked with a gantry. The gantry loader loads now the first process module. Here we apply the bonding layer, and on the right side, you see our layer thickness sensor. Now, when both sides have the bonding layer, the gantry grab the part and transfer it to the second station. In the second station, we apply the friction layer. So I would say nearly the same process. Again, with our layer thickness sensor, we have the option to have laser powers up to 24 kilowatt. So our process range are from 12 to 24 kilowatt. So after apply all 4 layers, the gantry system pick up the part and you as a customer only has now to pick up again the finished part, and it's a closed loop in our machine system. So after the 4 process steps, we have now the complete 4 layers, and we are ready for the grinding process.
Okay. During the movie, we received a question.
Yeah.
So we should answer that at first. The question is, what is the maximum hardness and temperature that the surface of the brake disc can reach after coating? Do you have comparative values for a conventional brake disc? So regarding the hardness, it's not easy to answer because we have 2 materials. The first material is the steel matrix, and then we have the carbides. And the hardness of the steel matrix is round about 200 to 300 HV, and for the carbides it is much more than 1000 HV. Temperature is
when we have now a dual layer system, we have normal surface temperature around 250 degrees. And this is also a reason why we need a cooling tunnel or a cooling system before we can go into the grinding process.
And the hardness value for the cast iron is, of course, less than the hardness of the bonding.
Yeah,
I guess.
Yes, absolutely.
So that leads us to the grinding process. This picture shows the surface after laser cladding. It is really rough, and the roughness depth is round about 100 micron. The reason for that is the carbide size, and in addition the influence of the coating process. That means the coating parameters. On the right-hand side, we see a typical measurement of run out after coating. So for the functional behavior in the brake system, a roughness depth of round about 5 micron is necessary. And sometimes the requirement is much higher. Not only the surface roughness, but also the macro geometry requires post-machining. Due to the energy input of the laser coating, run-out errors and form deviations could occur. A common target value for the actual run-out of the brake disc is 20 to 25 micrometers. So an additional machining process is necessary. For that, the EMAG answer is the VLC 450DG, our double disc grinding machine. The main features of this machine are the vertical main spindle with clamping chuck and with feed axis X1. Then the 2 vertical grinding spindles with feed axis Z1 and Z2. The workpiece shuttle with the workpiece lift on the left-hand side. Advantages are the excellent accessibility for setup and maintenance work. The grinding ships have no contact to the machining axis, and the simple workpiece handling. This movie explains the machine function in detail. It is made without using coolant in real life. Of course, we use coolant. So the machining lift puts the machined brake disc from the chuck and chucked in the rough brake disc, bring it to the machining area, and the grinding wheels get in contact with the brake disc. You see also our coolant nozzles. and now the machined brake disc is unloaded, and the process starts again with the next brake disc. One question. We received an additional question. What is the process time for coating?
It's a good question because it's not easy to answer. We have some influence like the laser power. As I mentioned, we have laser power beginning with 12 up to 24 kilowatt. And also the size of the brake disc has a huge impact. And it's depending if you have a double layer system or how thick your layer should be at the end. So I cannot give you a direct number. Normal process times are between 40 and 70 or 80 seconds. But yeah, when you have a sketch or drawing, please share it with us, and we can calculate cycle time directly for your brake disc.
Yeah, thank you. So, our next point is the quality requirement, the process chain, and in addition, the data management. This picture shows a typical brake disc and the demand for the quality requirements. On the right-hand side, you see the bases A and B. These are also our bases in our clamping chuck. The tolerance for the friction ring dimension, dimension C, is 20 microns. Also for the offset, dimension D, is also 20 micron. The requirement for the thickness variation circumferential is 6 micron and radial 20 micron. And for the phase run out, 25 micron. The achievement of these requirements is influenced by the quality of the pre-turned brake disc, the coating specification, the laser power, the coating process, that means energy input during coating, sequence of coating, thickness, and so on. We received a question: any data on rotor life enhancement in percent? Rotor life is the brake disc, lifetime of brake disc. What is written in the EU regulation?
Yeah.
Do we have an answer?
Again, it's not a fixed numbers. The lifetime in the Euro 7 regulation should be 8 years or 160,000 kilometers. So it's also written that all parts should reach this lifetime. So it should be like double, with the coating, we should double the life cycle. But again, it's not so easy to answer because we don't know which layer system you want to use, which car. And at the end, also the pads has an impact on the life cycle of the brake discs.
So about double the lifetime?
Should be double to fulfill the regulation, yes.
Okay. So the next picture shows a typical process chain for machining of coated brake disc. On the left-hand side, we see a typical turning line. At the beginning, we have the robot cell for loading the rough brake disc. Then we have 2 turning machines, and at the end, an additional robot cell for unloading the machined part. On the right-hand side, we see the laser coating machine and the grinding machine. Very often, those lines are not connected. Nevertheless, it's important to save and make available the production data of the complete process chain for each individual brake disc. In addition, we are often quote a measuring unit, a cool down unit, a washing unit, DMC reading, and so on.
So starting with the turning operation, we collect some data from the turning line. starting with the production parameters like feeding rate and turning speed, process data like X currents and temperature, or post-process measuring data like the geometry of the brake disc or the contact surface. Also, we collect the data from the coating machine. Here we normally collect production parameters like laser power, coating rate, the powder feeding rate, the X speeds, or the temperature, and sensor data like the layer thickness sensor of the base and the friction layer, the brake disc shielding, or information from the melt pool monitoring.
Yeah, and we also collect parameters and data from the grinding machines. The production parameters are feed rates, for example, grinding wheel speed and workpiece speed, and the process data are power and current of the grinding spindle, excess current of the feed drives, the contact position between grinding wheel and brake disc, and we could calculate the average grinding wheel wear per workpiece. So, what could we see here? We see a cut through a brake disc. And with the collected data, we are able to optimize the process chain. Above and below of the friction ring, we see the rough surface after coating. The blue area shows the tolerance field of the offset dimension. The black dashed line shows the tolerance field of the friction dimension. Both offset and friction ring thickness have a tolerance of plus minus 0.1 millimeter. Now we have added 2 yellow lines. The 2 yellow lines show the most efficient and resource-saving friction ring thickness. Why is this efficient and save resources? The friction ring is on the upper tolerance, so the lifetime of the brake disc is longer. We have a high coating thickness. We have removed less material by grinding. That means less time and less grinding wheel wear. So the aim for turning is a constant and optimal friction ring thickness. For the laser, a minimal material application, and for grinding, a minimal stock removal with higher layer thickness and within tolerance. The target across all processes is process quality with the highest efficiency. Resource efficiency means less coating application and less grinding. So we could collect all process data and can make the process react adaptively. Reduction of grinding wheel wear, reduction of production resources, time and costs, and optimization of quality. So possibly warping of the brake disc after coating is another challenge. The picture on top shows a brake disc in ideal conditions. The surface is flat with a low surface roughness, and the necessary removal by grinding is just a little bit more than the roughness of the coating surface. The picture below shows these brake discs in combination with the grinding wheel. If there is also warping, more machining is required. The minimum stock removal is high because of the warping. If we use high process forces for grinding, the brake disc follows the grinding gap and springs back again after machining. So the roughness is correct, the total actual run out and flatness are not. If the grinding is carried out with low forces, a suitable component geometry is achieved. but the friction ring layer has a wedged shape. As a result, the material efficiency of the process chain is poor, and the minimum laser thickness is easily undercut. Close coordination between laser deposition and grinding is therefore necessary. So the conclusion is cross-process optimization of laser and grinding process is required.
So here we have again our overview about the process chain, and what Marina mentioned, absolutely correct. We need to align all process or balance all process steps to each other to have the optimum. We need to collect machine data from the turning machine as well from the cladding machine to finalize on the grinding machine all information into a good process.
And for grinding, data from turning and coating processes are the basis for the optimization of tools and process parameters. So meanwhile, we received an additional question. Which is the average wear of the grinding wheels for each brake disc? That depends. That's always the answer. But we have already ground a lot of brake disc, and our answer is between 3 and 10 micron. That depends, of course, of the coating specification and so on, and of the stock removal. But I think 3 microns is a good number, 3 to 10 microns.
Yeah, absolutely. Because at the end, when you have a high grinding wheel wear, you have also high process costs. And we know everybody in the industry that we want a really low cost per piece production. And with a high grinding wheel wear, we never will achieve this requirement.
Okay, now we have collected a lot of data, and now we have to use them and transfer them to our IoT system. The solution for that is our ETMA workpiece data. So shown here is a rough infrastructure with data transfer to edge cloud. Each machine has its own IPC. We call it IoT core with ETMA Cortex. This IoT core records all data and provides also an interface for the customer network, for example. All mentioned data can be stored. The Data Explorer makes it possible to combine the data from each brake disc on one screen. Also, an export into additional data formats are possible, for example, CSV. With this data, you can compare workpieces and optimize the process.
Okay, now have a look on the results of the process optimization. We collect and grind a lot of parts in the past 3 years. So the data we show are from our laboratory. So I would say real-life data. As a cost breakdown of the coating process, the red line are the total cost per disc. The blue area are the process cost per disc, means machine hourly cost, tool cost, consumption cost, and worker cost. So everything depends directly on the process per disc. And the gray area are the costs for the powder loss. So the idle time or less powder efficiency. Here is a basic process with a layer thickness variation of plus minus 50 microns, powder efficiency with 85%, a layer thickness on the friction layer around 250 microns, and this leads to total costs above 13 euros. And you see we have a powder or a process loss of around €1, and process cost per disc are 12 euros and 12 cents. What we do in our laboratory or on our daily business, we want to optimize our process. In this case, we optimize our powder efficiency. A laser cladding process can have a powder efficiency up to 95%. But when we don't adjust the powder feeding rate or other parameters, we will increase our layer thickness. So with the same parameters but a higher powder efficiency, we will increase our layer thickness. This means our total fixed costs stay the same, but our process cost per disc goes up. So we start with our first optimization. We stay with our 95% powder efficiency process, but we lower the layer thickness again to 250 microns like required. And you see directly that this has a huge impact about the total fixed cost. So these are one of two steps we normally do. We first have a look on the powder efficiency and on the layer thickness. And the next steps are the average layer thickness. The gap now is not so huge, but still important because also with lower layer average layer thickness, we reduce our total fixed costs. And together with for the grinding process, we have a better input quality and also can reduce the cost for the grinding. And this is more or less the right thing to do. Make several iterations, optimize the coating process, and in the last one, we align both processes to each other.
These pictures shows a little bit when the cost savings by less stock removal. The red lines shows the high stock removal. The green line, the reduced stock removal. By that, we could reduce the wear of the grinding wheel and also the machining time. And at the end, we save machining time and we reduce the cost for the brake disc during the grinding process.
So with now both optimization on the grinding and the cladding side and the data we collect, we are able to reduce the surface roughness in combination with a lower shielding, results also in less grinding wheel wear during the grinding process. Shorter cycle time on the grinding and the cladding side through the lower layer thickness helps us also to save cycle time. In conclusion, the EMAG in-house process design results in a higher overall machine output and a reduction in the process costs. And these are for us a very important or the key feature in your daily production. We want to save with every process step money and powder to have the highest impact on your production. So all process steps need to be checked and balanced to each other. And this is for us the key for efficient and a cheap process.
So we received already an answer during the presentation. So we tried to answer this question. Does this coated rotor get along well? Different grades of PET friction material, or is there any restriction?
Yes. Normally, there are also different kind of brake pads necessary for the coated brake disc because you have different material mix. Therefore, you also need a different kind of brake pads. When this hopefully answers the question.
You could not use each pad to each coating specification.
No, absolutely not. Because when you look on the market, you have single layer system, you have tungsten carbide layers or titanium carbides, and therefore you need also an perfect matching brake pad for your rotor at the end, or for your layer system.
More questions? How many layers are necessary to fulfill the requirements of the Euro 7?
Well, a good question. I would say also a single layer system fulfill the Euro 7 regulations. So also when you only apply a single layer system, depending on your car size, you can reach the 7 milligram per kilometer, but it really depends on your needs or the car. When you compare a SUV or high performance car with a small vehicle, it's clear that you cannot use the same layer or same coating operation. So therefore we have these two options: single layers for smaller, lighter vehicles, and dual layer system for heavy cars or SUVs or something like this.
Of course, the single layers are much cheaper because the cycle time is less. But in some cases, in many cases, it is necessary to have a dual layer.
Yes.
According to our experiences. Next question. Do you also offer solutions for trucks or motorcycles? Up to what diameter can the components be coated and processed? So the name of the explained machine says that already. 450 millimeters is the maximum external diameter. And some of the truck brake discs are not bigger than 450 millimeter. But the shape of the truck disc are often completely different from the shape from the passenger cars. That's why we decided to develop a new machine type for the truck brake disc. And motorcycles, could you answer that question?
Yes, but I think motorcycles are not included in the Euro 7 regulation. So we don't see really a market for cladding and grinding of motorcycle brake discs. Nevertheless, the machine can coat and grind them. The question is if the market is ready for this kind of brake disc on the motorcycles.
Next question is, how is the quality of the coating checked?
Good question. The quality of the coating are checked in several steps directly in our machine. We have some sensors like melt pool monitoring or layer thickness. So we have already data from the machine or the machining process. But normally in the production after the coating, you have to cut some parts to check under the microscope the layer quality, check for cracks or pores. And after the grinding process, normally the brake discs go onto test benches to check the emissions or also the wear. But I think this is mostly during the development of the layers. So for your production, you have already our machine sensor data, and you have to cut every 1,000 parts or something like this. And then you are able to control your production batch.
We received an additional question. What advantages does it offer compared to conventional coating methods, galvanization, etc.?
Okay, yes, there are some options I mentioned in our presentation. There are other coating methods. We decide that we want to go in the direction of the laser cladding, because with the laser cladding, the experience shows that they have the best wear results, so also the longest cycle time. And with the material mix of the stainless steel and the carbides, we also have anti-corrosion function directly included in our process. So from our point of view, and also what the market shows, that laser cladding and grinding shows the best result on the cars and the test benches.
Okay. Oh, can you coat brake drums as well? Of course, we can do that, but not on the same machine type. For example, for grinding, the process is completely different because our VLC 450GT is a phase grinding machine, and for the drums, we need an internal grinding machine. We have machines for that, but it's complete different machine type. And for coating?
For coating, depends on the complete truck business. Truck brake discs has most of the time a different shape than passenger cars. So we always have to check some collision about the optic and the brake, the brake disc. And for the brake drums, it seems like this is really possible to do it already in our machine. But yeah, we have to check the drawings to see if there are any problems or collisions with the optics sensors.
So.
Okay, no more questions, Marina?
No questions?
Seems like. Okay.
Thank you.
Thanks for your attention, and yeah, see you next time on our EMAG webinar.